Okay, back to the whiteboard. We have spoken about string theory, 26 dimensions before. Now, the claim is you only need 11 dimensions. Then you need a supersymmetric particle to come to the theory of everything. Cosmology, inflation theory, rapid expansion at the beginning of the universe. Spoke about that. Causality. And the speeding up of the universe. 5 billion years ago, the universe started to speed up. Now, my theory now that I'm going to explains the rapid expansion of the universe, causality, the speeding up of the universe because of the cosmic shockwave. So the universe is speeding up because of the cosmic shockwave. So my theory was never proposed before I did, and now we're going to explore it a little briefly, and let's see what we get. Oh, and homogeneity is going to be explained by the cosmic shockwave also, because that smoothed out the universe. So the cosmic shockwave is going to explain homogeneity and the speeding up of the universe. So, so the main thing is now I'm going to talk about where exactly were these particles created, exactly where at the beginning of the universe. So I've used words like AIN, which is almost an infinite number. AIP, almost infinite period, because we cannot have infinity because we are here. And if there was infinity, we would not have been here. AIE, almost infinite energy. AID, almost infinite density. And AIP, almost infinite pressure. So these two terms come from the singularity, as they would call it. Okay. So I spoke about the cosmic cake. Well, I'm running out of thing. So the cosmic cake, for us to be here, there had to be a perfect cosmic cake that was made for this universe to look like what it is. So actually, cosmic cake is what we see out there in the universe for us to exist. It had to be perfect. So it took almost an infinite number, well, we're gonna put years behind that, or almost infinite time, for the cosmic cake to really form in the right way. Now, at the beginning, we had almost infinite energy, with an almost infinite density, with an almost infinite pressure, and that's what they call a singularity, right? And that exploded, and that banged, and this is where we came from, this universe. That's the cosmic cake. So we're going to talk about although some of these markers work, we are running out of marking fluid. All right. So now we're going to get into the nitty-gritty. And this is my theory is an amazing theory. I mean, it explains pretty much everything that's not explained right now in the universe. It explains practically everything. So, all right, let me just get rid of this rubbish. So now, we have the singularity. This is before the Big Bang. This is energy, almost infinite energy, with almost infinite density and almost infinite pressure. So something happened, and I call whatever happened the big pulse, because the big pulse is going to explain cosmology, inflation theory. So we had a big pulse first. So this pulse, so it will pulse inward, right? So this pulse inward, this is the original singularity, and it pulses inward. Why would it pulse inward? Then there should be a force out here that, you know, that would be acting on it for it to pulse inward, right? There was a pressure acting on it, and then it pulsed inward. But we'll get into that in the future, what could cause it to pulse. But it pulsed inward. When it pulsed inward, this is the original singularity. I have to call it a name, so I'll call it singularity, original. So it pulsed inward to here, to this shape, a smaller, small volume, but higher energy level in here. Very important. This is a higher energy level, very important. It pulsed inward. So when it pulsed inward, that means we have a different energy level here, right? A different energy level here. And it pulsed inward, but when it pulsed inward, it shoot off some of the energy out here. It has to shoot out. For action, for every action, there's going to be a reaction. It pulses in, as it pulses in, it shoots off a weaker and not weaker, a less dense energy in the sense of it's kind of a diffuse energy, but it shoot that out, right? This energy here. So in between here and here, where it pulsed, we have a force and elementary particles of a certain property. See, this is why exactly, I'm telling you where exactly in the Big Bang these forces and elementary particles were created. So now you've seen how this occurred, where exactly, and no one has ever proposed this. So it pulsed. We now have a different energy level here. A low energy level is going to be going out here. Slightly higher energy level is going to be here. And the highest energy level is going to be here, right? So we created an energy level. And so it pulsed inward. I believe what I had meant to say was that it pulsed outward first, right? It pulsed outward. Oh, everything is falling. I believe I said it. Well, I believe I was supposed to say pulse outward first. We had a big pulse outward, right? So if we have a pulse outward, right, this would explain, so this would be the original singularity here, the smaller circle, and when it pulsed outward, between here and here would be the exponential inflation, right? Here and here, it expanded rapidly, right? The universe expanded rapidly between this small amount of time, and this is where cosmology inflation tried to explain with a different theory. So it pulsed outward first, created that rapid expansion, it collapsed back in because of the forces acting here, and then when we, well, don't forget that a lower energy level was kicked out, right, when it pulsed. So now we have an energy level that's shooting out, right? So it pulsed, and then a force out here kept it from going forward. So when it pulsed inward, so when it pulsed outward, we're going to have certain particles that were created here with certain energy levels and certain fundamental forces, like say the electromagnetic force or the weak nuclear force. I will get into that in the future. And then it actually expanded, right? And that's where the Big Bang really really started, the real expansion. So it pulsed, and we had rapid expansion, the force acting on it, keeping the singularity in place, push it back, right? And then it pulsed again. So pretty much it's 3 times. We have an inward pulse, an outward pulse, an inward pulse, and a third pulse outward. So obviously we're going to have 3 fundamental forces, pretty much, 3 elementary particles, but with different properties. We're going to have 3 elementary particles, but a family of them. Because you have to remember when you're going in and out, and you have a different energy level, would create different elementary particles and elementary forces, right? And then we have gravity, which I'm going to talk about today. But now we have these fundamental forces, and don't forget, we have the original, when it first pulsed, this energy was thrown outwards at the beginning. That's the first energy level that was thrown out. So now we have 4 fundamental forces without counting gravity. And I calculated that we're going to have, we have more particles than we see in a standard model because of this theory. Way more, right? You're going to have the particles, but you're going to have a hierarchy particles, because you're going to have one particle, but they're going to have a family of particles because of these zones. And this is what I call them, the zone. There's a zone here, a zone here, a zone in here. And then when you go in different directions, you're going to have different energy levels. So you're going to have different particles, different zones, and so on and so forth. So that's the fundamental idea behind my theory. Right? So you're going to have more particles, more forces, and different levels of forces. You're going to have weaker forces. So where's the proof? How can I prove? Briefly, I'm not going to get too much into it. Right? This is just a beginning of showing you how a lot of all this physics questions can be answered. Right? This is new physics. Right? This is actually new physics. Let's talk about what this force is going to be like. The exterior force, the most exterior force. It's going to be weak, right? And it's traveling out there. Now, when these particles started, the forces started to now form when the universe started to cool. The forces now is going to come into play, particles and stuff like that. But this weak force is there, and we need to find this weak force, right? The cosmic shockwave will come when this part of the universe expanded and catches up to this weak force that's traveling outwards. Right? My pen ran out. So it's traveling outwards. The cosmic shockwave would run into this zone of weak force and push it faster. And 5 billion years ago, it caught up with this weak force, and this is why the universe started to expand rapidly. Right? That's the idea behind the cosmic shockwave. And it also will smooth out the universe, so it would look homogeneous, all the way around the universe because of the cosmic shock wave. So that solved that problem also. So this solved the rapid expansion, the exponential expansion at the beginning of the universe. It explains the speeding up of the universe, and it explains that there is other forces out there, and they explain exactly where these forces were created. Let's take, for example, the center here, which has the highest energy level. So what particle would be created here? The proton would be created here. I mean, it would not be created here, but the properties created the proton and the neutron would be created here, because these two particles would need the highest energy level, and this is where the highest energy level would be. Right? Because to form the proton and the neutron, you gotta have a strong nuclear force, and this is where the strong nuclear force, which is one of the most fundamental force, one of the four fundamental forces, were created. I'm sweating, starting there. So that's where that strong nuclear force will be created right here. So I'm showing you exactly in this zone it will be created, right? And the force carrying particle, which is a gluon, right, which glues the quarks to form the proton and the neutron, will be created here. So the gluon and the strong nuclear force, not created, but the properties of these two. One is an elementary particle, and the other is a fundamental force, will be created here, right? So when these properties cool down, we form the proton and the neutron, right? Binds it together. Gluon binds the quarks together, and it creates the neutron and the proton. Proton. So I'm showing you exactly where these particles and forces were created. Okay. Where were the magnetic force will be created? In one of these zones, right? Because we have this zone, we have this zone, and then we have the contraction and the expansion in this zone. So in these zones, I'm not going to get into that as yet, will the electromagnetic force be created, right? And the weak nuclear force in these zones. And of course, electromagnetic force, right, merge are two forces, electricity and magnetism. So there have to be some kind of interaction, some correlation in one of these zones, right, to form the electromagnetic force. So this is the first time you're going to hear exactly where these particles were created. So I'll go in depth. I'm going to choose a topic again, and then I'm going to show you exactly where these other forces and particles were created. The bosons, the mesons, the leptons, why particles have spin, why they have charge, of course. Because if you go in one direction and then suddenly you have to go in a different direction, the one particle, is going to have, the one family of particle is going to have, one particle is going to have a different family of particle. Because you go in one direction, you have to stop, then you turn around, you have to go into a different direction. So you're going to have different properties, and you're going through different energy levels. So this is a hierarchy problem of the beginning of the universe, and the generational, why particles are generational, right? This solves why particles are generational. For one particle, you're going to have a family of particles, right? All it means is that the properties are just going to change, but it's just one particle created in a zone, have to go in one direction, travel in the other direction, with slightly different energy levels. So that'll explain that. So in conclusion, we know that we're going to have more forces, more particles created, right, because of the different energy levels. And we'll continue with that point. So I'll leave this point at that, because I would have to go through this over and over and over and over again because, my pen ran out of ink. So the question I had asked is, one of the questions I asked is, if we were to take all the rubbish out of this universe as we know it, with light travel at the speed of light as we know it now. So that's a question. So in this dark verse, which you cannot see, right? This is our visible universe. Will light travel faster than the speed of light up here? Right? In this dark verse. The hint is we have this force, right? That's actually going through the dark verse right now, being propelled by these forces, by the shockwave forces, right? They're being propelled by the shockwave forces, right? So when we get into the dark verse with this weak force, maybe we're gonna have now we're gonna talk about gravity, right? Gravity may be now so powerful that light may not travel as fast as it does here, it may travel faster than that. And of course, when the shockwave reached up with this weak force, it pushed the expansion of, it speeded up the expansion, right? Because it speeded up because as we know, 5 billion years ago, the universe, it started to rapidly now speed up. So this is where the dark energy comes from, right? When we talk about dark energy, it's because of this shockwave force that now is now reached up to this weak force and push it, accelerating it. So the shockwave force now is accelerating this weak force out here, and this is why we have dark energy. So that's the explanation for dark energy. Not only one explanation, but we have to take into consideration that they out here now, we have these forces out here that could be also pulling on our visible universe, right? Pulling and increasing it. Obviously, it's expanding it, but it could also, be a factor in the increase and the expansion. So these are very important. This is a very important theory, and in fact, I'm going to use this theory and see what I can do with it. And this theory has been copyrighted for over 10 years. So it's not like I came up with this theory yesterday. It is copyrighted, and some words will be copyrighted. But it's the first time I decide, hey, try to put it out there and see who wants to comment on it, and see if it's viable. And to prove this weak force, right? We can prove this weak force if it exists, because what's around us here on Earth is not going to be what's out there on Earth, right? This weak force could be weaker out there, say by the moon. Just give you an example, right? It could be weaker there, right? Because it's being diffused. This force is being diffused, but it's there. Right? And if this force interact with, say, a field like the Higgs field, we can have virtual particles occurring in and out, coming into existence, and then decaying. Right? It's possible. This weak force is responsible for the virtual particles. To prove the double slit experiment, we should take the double slit experiment towards the moon, right? And there may be a difference in this weak force than it is on Earth. So when you do the double slit, experiment, you're going to see a different result from close to the moon than it is on Earth, right? Because of the diffusion of the weak force. So that I propose you can possibly prove this weak force exists. Or as far away as you can from Earth, it's going to be different. Now what it is here, so the farther out there you go, this weak force is going to be diffused. With sensitive instruments. If you go close to the sun and you do the experiment, you're going to see a difference, right? All right, so I'll leave it at that. Gotta get some ink for my pen.